Good morning, sir. My name is Anjali Goenka, and the topic of this presentation is the vacuum distillation. The contents in this slide are following. First is distillation, then the next is what is vacuum distillation, the applications of vacuum distillation, which is further bifurcated into laboratory scale applications and vacuum distillation in petroleum refining. Then, when is it used in the petroleum refining? The process steps which are being followed for the vacuum distillation, the products obtained from vacuum distillation, advantages which we have of vacuum distillation, and the challenges which we face due to vacuum distillation, and at the end there is summary. So let's start with distillation. It is a process of separating the components or substances from a liquid mixture by using selective boiling and condensation. There are some following exceptional styles of distillation. First is fractional distillation, then vacuum distillation, superfractionation, thermal cracking, and catalytic cracking. Among these five, we will mainly focus on vacuum distillation only, as it is the part of this presentation. So the question comes is, what is vacuum distillation? It is a method of distillation only where the pressure above the liquid mixture to be distilled is reduced to less than its vapor pressure so that the evaporation of the most volatile liquid can occur. The most volatile liquid here represents the liquid with the lowest boiling point. This distillation method of vacuum works on the principle that boiling occurs when the vapor pressure of a liquid exceeds the ambient pressure or the surrounding pressure. This vacuum distillation also permits the distillation of liquid that are temperature sensitive and avoids any degradation of such liquids. Now, next slide comes is of applications of vacuum distillation. So mainly laboratory scale applications are there and industrial scale applications are there. Laboratory scale applications include rotary evaporation and safety consideration, while industrial scale applications include vacuum distillation in petroleum refining. First of all, we will go through laboratory scale applications. It includes rotary evaporation, in which rotary evaporation is a common technique used in the laboratories to concentrate or isolate a compound from the solution. Many solvents are volatile and they can easily be evaporated using rotary evaporation. Even if the solvents are not very much volatile, they are somewhat less volatile, they also can be removed by rotary evaporation under some specified condition, that is of high vacuum and with the heating. This rotary evaporation is also used by the environmental regulatory agencies for determining the amount of solvents in the paints, coatings, and inks. Second is our safety considerations. Safety is an important consideration when glassware is under vacuum pressure in the laboratories. The scratches and cracks can result in implosions when the vacuum is being applied there. So wrapping as much of the glassware with tape as is practical helps to prevent dangerous scattering of glass shards in the event of an explosion or implosion. Now next topic is of industrial scale applications, which includes vacuum distillation in petroleum refining. So the almost 80% of the refineries operating in the United States have a vacuum distillation unit, which is also known as a secondary processing unit after atmospheric distillation unit, and it is consisting of vacuum distillation columns. The vacuum distillation is a part of the refining process only, which helps to produce the petroleum products out of the heavier oils which were left over from the atmospheric distillation unit. The vacuum distillation can also be referred to as low temperature distillation because the temperature being used in the vacuum distillation is somewhat lower than comparison of atmospheric distillation. Now, the questions come is, when is it used? If we are already having atmospheric distillation unit to refine our products, then when vacuum distillation column is being used? So in the refining process, the atmospheric distillation unit, also known as ADU, separates the lighter hydrocarbons from the heavier oils based on the boiling point. And here the ADU is capable of boiling crude oil functions to temperatures of 750 degree Fahrenheit. If the temperature is above 750 degree Fahrenheit, the oil will thermally crack or break apart, which impedes the distillation process. And as the lighter products are boiled off, the heavier oils left at the bottom side, which are also known as bottoms, remain at the bottom of the ADU. Now, to increase the production of high value petroleum products, these bottoms are run through a vacuum distillation column to further refine them. So, this is where the vacuum distillation column comes in picture to increase the production of high value petroleum products of the ADU. Now, as the name vacuum distillation implies, the distillation column is under a vacuum or significantly less than atmospheric pressure of 760 millimeters of mercury. And at the low pressures, the boiling point of the ADU bottoms is low enough that lighter products can vaporize without cracking or degrading the oil. Hence, vacuum distillation is giving us two main advantages. One of which is that it provides lighter products without cracking or degrading the oil, and other is that it helps in converting the low valuable petroleum products to the high value petroleum products. Now next come is process steps of vacuum distillation. What are the steps being followed while vacuum distillation? The reduced crude oil, that is our bottoms of ADU, is being pumped through a series of heat exchangers and a crude furnace until reaching the desired temperature, that is from 350 degrees Celsius to 390 degrees Celsius. The reduced crude oil is flashed to separate the desired fractions. The light vapors are raised to the top and heavier hydrocarbon liquids fall to the bottom side of the vacuum distillation. Steam injection at the bottom of the column improves the separation of lighter boiling components, and the vacuum column uses a series of pumps around to maintain temperature at the correct level at certain points along the tower. Light vapor gases are removed at the top of the tower. They are being condensed and recycled back to the column as reflux. Here, light vapor gases are removed from the top of the tower as they are light in weight, and normally the vapor rises in the upward direction, so they are removed from the top of the tower, and the heavier vapors or heavier hydrocarbons are being removed from the bottom of the side, and the light naphtha that is being drawn off, and excess gas is sent to flare. The vacuum gas oil and the lubricating oils which are being produced from vacuum distillation are drawn off and routed for further treatment in the hydrotreating units. And the vacuum residue which is being obtained at the bottom side of vacuum distillation is sent to intermediate distillers or to be further processed in a FCC or delayed coking unit. Here FCC is also a unit which is fluid catalytic cracking. So the bottom products are being sent to different units for further processing to make them more valuable high petroleum products, that is hydrotreating unit, FCC, that is fluid catalytic cracking unit, and delayed coking unit. Now the products which we obtain from vacuum distillation. So as you can see in this picture, vacuum distillation is being shown in this picture, and the atmospheric column bottoms are being fed as feed in this distillation, and light vacuum gas oil, heavy vacuum gas oil, slop, and vacuum column bottoms are different products which we obtain from vacuum distillation at different boiling points. And these are the temperature and pressure. At the top side of vacuum distillation, the temperature is around 150 degree Fahrenheit and 10 mmHg, and at the lower side the temperature is around 750 to 770 degree Fahrenheit and 20 mmHg. Now the vacuum distillation produces several types of gas oil, as we have already seen in the previous slide. Light vacuum gas oil, high vacuum gas oil was there, and these are slightly heavier than middle distillates such as jet fuel, kerosene, and diesel, as these different middle distillates are being further processed using hydrotreating unit or FCC or delayed coking unit. And in the next stage of refining, these gas oils are further refined to make products such as light cycle oil, also a type of distillate, gasoline, and naphtha. And one such refining process is fluid catalytic cracking. Now next is our advantages of vacuum distillation. So the first advantage which vacuum distillation gives us is it reduces the number of stages needed. It also allows for distilling heavier metals at lower temperatures than those that would be required at atmospheric pressure, and thus it also helps in avoiding thermal cracking of the components which generally occurs at atmospheric pressure. It improves the separation by increasing capacity, yield, and purity. It has the reduced capital cost as well, but at the expense of slightly more operating cost. Now the next is our challenges which we faced in the vacuum distillation. Normally these challenges are being faced in all type of distillation process. The first is that the temperature fluctuations may occur and that could affect the rate of evaporation. Similar goes with the pressure. If the pressures in the pump can gets fluctuated, it will also lead to similar complications, that is affection in the rate of evaporation. Next, let's recap all the topics which we have discussed in this presentation. So mainly the vacuum distillation is being used in the petroleum refining only, so we have discussed that part. The atmospheric residue which we have obtained or got from atmospheric distillation unit, when processed at the lower pressure, does not allow decomposition of the atmospheric residue, and therefore it yields LVGO, HVGO, that is light vacuum gas oil, and high vacuum gas oil, and the vacuum residue. The LVGO and HVGO are eventually subjected to cracking to yield even lighter products. And the video consists of a main vacuum distillation column here, supported with side strippers to produce the desired products. Therefore, video is also a physical process to obtain the desired product only. And the operating conditions at which video works is the pressure that is being maintained about 25 to 40 mmHg, and the temperature should be kept at around 380 to 420 degrees Celsius. Thank you. That's it from my side.